So when we talk about something being normally distributive, I kind of hinted that the mean, the median, and by the way, the mode would all be about the same value. So what would happen is the mean would be in the middle of this curve, and from there, that would be the mean, median, mode because it's the tallest. Second part about this curve is it's symmetrical on both sides of this mean, where the dotted line is, and half of it is on the left and literally half of it is on the right. And one of the other things you need to know is the area underneath this curve, which is really kind of cool, is equal to 1 no matter what the shape of the curve looks like. For instance, right now I have the standard deviation set at this number and the mean set at this number. So if I change the value of the mean, basically all that happens is the graph slides so that the mean lands where it needs to. So if the mean is 5, we're at 5. If the mean is 4, we're at 4. And therefore the curve just goes with it. All right, let's put it back to 5. And then the standard deviation has an effect. So the standard deviation, these values here, this weird symbol plus another weird symbol, I couldn't get on my this text here to make x bar and then plus s wouldn't make sense. So this is actually mu plus sigma, and mu happens to be the mean. Sigma, I showed you earlier, represents the standard deviation. So basically what this means is if we're at the mean of 5, then with a standard deviation of about 1, mu plus 1 is going to give you 6, mu plus 2 is going to give you 7, mu plus 3 is going to give you 8. So this is known as one standard deviation from the mean to the right. And then if we go the other direction, that would be one standard deviation from the mean to the left. And then if you just say one standard deviation away from the mean, that's anything from 4 all the way up to 6, because it's 1 to the left and 1 to the right. And the same thing goes for 7 and 3. They are 2 standard deviations away from the mean. And then 2 and 8 are 3 standard deviations away from the mean. And I'll be drawing on a picture so it's a little bit more clear. So now if I change the standard deviation, what will happen is if I make it smaller, those numbers are going to get closer together, representing that the average distance from the mean is a small value. And then to accommodate that and keep the area of 1, the curve has to get taller. So as we make the standard deviation smaller, the curve is going to get narrower. The numbers are going to get closer, the 1 standard deviation away, the 2 standard deviations away, and the 3 standard deviations away are going to get closer to the mean also. And eventually it's just going to go off my graph and create this really tightly packed bit of information. Now let's go the other direction now. Back to 1. There's 1. All right. Now if we go the other direction where the data is more spread out, more dispersed, then the curve has to come down to account for numbers being spread out more. And the standard deviation is pushing the distance away from my mean. So now 1 standard deviation away from the mean is bigger than 3 and between 2 and 3 and between 7 and 8, where before it was, 4 and 6. So as the standard deviation gets even bigger, the curve basically almost flattens out. But the area underneath it is still going to be equal to 1, going all the way to the left and all the way to the right, which is one of the cooler features of this curve. Now, this means that I can make the mean anything I want. So this curve can be located almost anywhere. And that just becomes a headache later on. It's nice to be able to describe things with it, but it would be really nice if we just had one curve that fit all situations. And that's one thing we're going to be heading for. So when we have a situation where the data is normally distributed, for instance, these two pictures are the graphs of the normal distribution of the heights of women and men in the United States. You can see, of course, the average height of a woman and the average height of a man are, well, different. And I got these scales perfectly lined up. So you can see that men are generally taller than women. But not all men are taller than all women. Kind of a neat little breakdown. So if we drop this down and this up, we can kind of see where um, the average height of a man is about 3, 4 inches taller than a woman. So, there's some neat information here. And you can also see the standard deviations. Here, the standard deviations are to the left there and to the right here. And you'll notice on the men that the standard deviations is a little bit further apart. The standard deviation for men is about 3 inches, where the standard deviation of women is about 2.5. And you also notice that the curve, the red one, the first one, is taller than the men graph. And that's because of that smaller standard deviation. So another thing that we want to talk about is if a person, what is the probability that a woman is within one standard deviation of the mean? So I want to be able to know how many women are we talking about that are somewhere between 62 inches and 67 inches tall. So this would be 62 inches all the way up to 67 inches. And the cool thing is that it matches up perfectly with the exact same answer as the number of men that are between 66 inches and 72 inches. It's the same probability. So this idea that you're one standard deviation away from the mean has an equal probability for the men and the women, even though the curves are slightly different looking. So remember, the area underneath the entire curve is 1 for both of these, even though they look different. So that's one thing I want to talk about. I want to be able to talk about what percent of people are between women between 62 inches and 67 inches, and what percent of men are between 66 inches and 72 inches, better known as one standard deviation away from the mean. So one of the first steps of trying to understand exactly how much information is, close to the mean, a little bit further away from the mean, and so forth, is this rule, which is called the 68, 95, 99.7 rule. And the numbers are actually kind of important. The 68 represents one standard deviation, the 95 represents 2 standard deviations, and the 99.7 represents 3 standard deviations. So it pretty much gives you a clue on how this thing is going to work. So let me give you some pictures, and then we'll talk about breaking them down a little bit. So here's a picture of what it means by 68 in the 68, 95, 99.7 rule. This here, if it's hard to read, is x bar minus 1 standard deviation, and this one here is x bar plus 1 standard deviation. So we are 1 standard deviation away from the mean, which is here. This would be x bar. Okay. So what it means is if you are within 1 standard deviation of the mean, the probability that you are in that shaded region is 68% of the time. So if we go back to the women and men, we find that 68% of the time you will find a female between 62 inches, which is 5'2", and 67 inches, 5'7". That 68% of the population is between that. So if you are above or below that 68%, then you would be, average. Average is in the middle, so you would be above average or below average depending on what side of this graph you are. So if you're someplace over here, you would be considered above average, and down here, of course, below average. Now, men, similarly, 68% of them are going to be between 66 inches and 72 inches because it's one standard deviation away from the mean, which is 69 inches. All right. So another thing that's good about this picture is notice the little dotted line I have going down the middle of this graph. That cuts the area perfectly in half. So on this half, there is 34%. And on this half, there is also 34%. We can even break it down a little bit further and go into what is the percent in this part and what is the percent in this part. Well, if 68% takes up the middle part, that leaves, let's see, 100 minus 68, that would be 2, that would be 32%. So 32%, but it's getting split into two equal pieces. So this side would be 16%, and this side would be 16%. So just knowing that the middle 68% is one standard deviation away from the mean gives us a lot of other things that we can look at. What is the probability that you are greater than one standard deviation above the mean? And that would be a 16% chance. 16% of the population of women is taller than 67 inches. And the same thing goes for the bottom 16. And then you can say, well, what's the probability of a woman being 64 and a half inches to 67 inches? And that answer would be 34%. So this one number gives us a lot of information based on the idea that the graph is symmetrical by the mean. Generally, I only go up to 95% because after that, it's just the same old, same old. So if we go to 95%, notice over here off to the side, it says 2 standard deviations away from the mean. So this distance is 2 standard deviations, and this distance is also 2 standard deviations. So you are within 2 standard deviations of the mean. And the same thing's going to happen. 95% of the population is going to be between 2 standard deviations of the mean. If we cut it in half, then each half would have 47.5%. And if we looked at these are called tails, by the way. So this is a tail. In the tails, what's going to be left is a split of 5%. Because if you do 100 minus 95, you're left with 5%. But that's 5% to the left and the right at the same time. So you have to cut that in half. So you get 2.5% down here and 2.5% here. So that means, if I go back to my females, this is 66 and a half right here. So that would be 5 foot, basically 5'7". So that means the probability of a woman being taller than 5'7" would be 2.5% of the time. So in dealing with this normal curve, the mean can be anything. So that kind of, gives us different pictures for each situation. And I'd rather just one picture for every situation. So one thing that we're going to do is we're going to try to create a nice numerical scale. So for instance, here's our mean. This is X bar. It's 69 inches for the men. And one standard deviation above it is 72 inches. That would be this number right here. So I would want to represent the mean, instead of, 69, I'd rather represent it by 0. And one standard deviation away from the mean, I'd rather represent that by 1 to represent one standard deviation above the mean. And therefore, 2 standard deviations above the mean would be 2. And then on the other side, this would be -1. This one would be -2. And this one would be -3. It would just make sense. that if you're positive, you're above the mean. If you're negative, you're below the mean. All right. So one way to make 69 equal to 0 is literally just to go, well, I have this 69 as a mean, and I'm going to subtract it from itself. So what we're going to do is we're going to call that x minus x bar, where x is the number we're looking at, which is 69, and the mean of the data is x bar, 69, and that would become equal to 0. Now, how would I get 72 to be replaced with 1? Well, if I take 72 and I subtract 69, the answer is 3. And the standard deviation of this data is 3. So if I want it to be equal to 1, I would take this and divide by 3 would be the easiest way to do it. So the formula I'm going to use that you have to memorize is we're going to call these numbers z. So the -3, the -2, the -1, 0, 1, 2, we're going to represent them with z's. And z is going to be the data point we're looking at minus the data's mean divided by its standard deviation. And this formula creates what's known as the standard normal curve. So you can take any situation and force it into a single picture. So let's put these two ideas together using the 68, 95, 99.7 rule and the formula z equals x minus x bar over the standard deviation. Because they kind of interrelate to each other. One of them is talking about standard deviations away from the mean, and the other one tells you standard deviations away from the mean. So let's look at this problem. I actually looked all this information up on the internet. The average height of a woman in China is 5'2", a little short, with a standard deviation of about 2 inches. What is the probability of selecting a random woman from China and her height actually being between 4'10" and 5'6"? Now, one of the things that is really bad about, measuring people as 5'4", 5'6", is it's two different measurements. It's not like it's 5.2. That would be nice if there was only 10 inches in a foot, but there's 12. So one of the first things you have to do with heights that are measured this way is to change them into inches. So 5'2" is 5 times 12, which is 60. So this would be 62 inches. 4'10", 4 times 12 is 48. So 10 more would be 58 inches. And then 5 again is 5 feet is 60 inches. So this would be 66 inches after you added the 6 more. So these are the numbers we're going to have to work with, and then, we can answer the question. So before I go anywhere, this value up here, the 62 inches, this is x bar. And then over here, the standard deviation of 2 inches, that's s, which, in the formula for x minus x bar over s. So these two other values that I want to be between are going to be x's. And I'm going to call the first one x1 and the second one x2. So to use the 68, 95, 99.7 rule, you just need to know how many standard deviations away and where exactly are they located. Okay, so I'm going to use z equals x minus x bar twice over s because I have an x1 and an x2. So the first one I'm going to call z1, and x1 is equal to 58. The mean is 62, and the standard deviation is 2. And then simplify. So z1 is going to equal, so 58 minus 62 is -4 over 2, better known as -2, which makes it 2 standard deviations to the left of the mean. So this is 2 standard deviations to the left of the mean. Okay, and we'll do the same thing for Z2. So Z2 is equal to 66 minus the mean, 62, divided by the standard deviation of 2. So Z2 is equal to 4 over 2, which is equal to 2. So this is 2 standard deviations to the right. Now, if you're within, and this is within because you're going left and right, then the percent is going to be, when we look at, let's go back to my beginning color, 68, 95, 99.7, then 2 standard deviations to the left and to the right is the middle number because it's the second number. So the percent of women in China that are between 4'10" and 5'6" is 95%. Almost all of the women in China are between those two heights. Pretty cool what we can do with this stuff. Using the exact same example of the Chinese women with the same mean height of 62 inches and a standard deviation of 2 inches, I want to know what the probability of a Chinese woman being between 62 and 64 inches. So again, this is going to be x1, this one is going to be x2, they're my data points. This, of course, is my x bar, this, of course, is my s. So I'm going to have a z1, which is equal to x minus x bar, over s. And when I put in the numbers, my x is 62, my x bar is 62, and my s is 2, and the answer here is 0. Because 62 is the mean, I would expect an answer of 0. Z2, on the other hand, is going to be 64 minus 62 over 2, and we're going to get 2 over 2, which is 1. So this is 1 standard deviation to the right. So I'm not within 1 standard deviation of the mean, I'm literally just 1 standard deviation to the right. So the picture that comes into play is the 68% picture, but the answer is not 68% because we are only dealing with the graph to the right. So we're only dealing with this portion of the graph, which is half of the 68%. So from 0 to 1, we're going to be getting 34%. So this would be 34% of women are between 62 inches and 64 inches. And that would be the answer to our question. Now that rule, the 68, 95, 99.7 rule, is the beginning of finding percents using a normal curve. But over time, people have gotten better calculations on how much area is between almost any values you can imagine on a normal curve. So the way the table is going to work is you're going to find your z, whether it's positive or negative. I always draw it on the positive side, but it really doesn't matter. And the table works this way. It finds the percent, or the probability, that you will be less than z. So the table is always built on less than z. So if this less than z turned out to be, let's say, 80%, then greater than z is going to be 20% because the whole curve has to add up to 100%. So one of the more simplified tables looks like this. And the way you're going to read it is if you ended up with z equals negative 2.3, then the probability of being less than this z value is going to be given by, you look up negative 2.3, which is here. This first column is a z-score. So our negative 2.3 is here, and next to it is the percent of information less than a negative 2.3 z-score. So a negative 2.3 is like way out here on my curve. We are negative 2.3 standard deviations away from the mean, and the amount of area under the curve less than negative 2.3 is 1.07%. Now, what does that mean about bigger than z? Well, bigger than z, there's two ways to go about it. Number one, we know that the bottom portion is 1.07%. So the top portion, since the whole thing has to add up to 100%, the top portion has to have 100% minus 1.07%, because the two halves have to add up to 100. 100 minus 1.07. 98.93. 98.93%. So that would be those greater than z equals negative 2.3. And then the other side is always going to be less than. And that's what the table gives you. It always gives you less than z equals negative 2.3. So when working with this table, there's I have negative 2.7 all the way up to positive 2.7. You'll notice I also don't put 0 in the table because 0 is equal to 50%. It cuts the graph into two equal pieces. And it saved me some room when I created the table. So with this problem here, we have Mr. K's last math test had an average of a 62 with a standard deviation of 13 points. So what I want to know is what percent of the students that scored at most a 70. So that would be a 70 and below. So that's another way of saying less than or equal to 70 at most. All right, so how are we going to tackle this problem? Well, it gives us enough information that I can find a z-score. So z is equal to x minus x bar over the standard deviation, x bar, of course, being the mean, x being the data point. Now, the data point is 70. The mean is the same thing as this word up here that gets commonly used, is the average, which is 62. And the standard deviation is 13 points. So this becomes 8 out of 13. 0.615. So I'm going to write it as 0.62 and go from there. So this is 0.62. And this number here, this z-score, has to be written as a decimal because we're going to use the table. Now, to emphasize a few things, if we drew a normal curve, and I implore you that you might want to, it doesn't have to be a pretty picture. 0 is the mean, so that would go here in the middle. And 0.62 is just someplace over here to the right. So what it's asking for is the probability of this shade. Now, as long as the shade is going in this direction, you look at the table directly for an answer. You don't have to do any other calculations. So if we pull up the table, the closest value to 0.62 is 0.6. So this table is only based on a z-score of the nearest tenth. So for the table, you only have to round to the nearest tenth. There are better tables out there. They're just a little bit more difficult to read. And this is close enough for our work. So the percent that we're looking at is 72.57. So the answer to this question is 72.57%. would score at most a 70. At most a 70. So if I change my question and I say percent at least a 70, now we have to do some calculations on the side. So this number represents the percent below a 0.62. What I'm interested in is the percent above 0.62. So to have greater than or equal to 70, we're going to have to find its complement, which is 100 minus 72.57, which is 27.43. So it'll be 27.43% of the students would score higher than a 70. So this is how we use z-scores and this table. So it's either a direct answer, which is smaller than, it's 100 minus the answer if it's bigger than, and that just leaves one more possibility. All right, so let's use the same example, basically. The average of a 62 and the standard deviation of 13. And then what I want to do here is find the probability of a student having a score between two specific test scores, a 37 and a 67. And kind of like what we were doing with the 68, 95, 99.7 rule, is we're going to designate these two x values as x1 and x2. So we can distinguish which one is which and, kind of keep things straight. So that, of course, means we're going to be looking for a z1 and a z2. So the formula being x minus x bar over s, we're going to let z1 be this first x1, which is 37. The standard deviation is 62, and we're going to divide by 13. The setup for z2 then is going to be 67 minus 62 divided by 13. This one is actually easier to calculate in my head. This is 5/13. That one I'm going to have to work on. So z1 is negative 25 divided by 13. All right, so back to here. Negative 25 divided by 13 gives us negative 1.9. Remember, we only need to the nearest tenths for this table. So this one is negative 1.9. And then 5 divided by 13 is 0.4, closest. So this is z2 is approximately 0.4. And then we'll look it up on the table. All right, so what we're looking for here is if we drew the graph, we'd have our little normal curve. It's not too bad. Here's 0. Negative 1.9 would be someplace to the left. 0.4 would be someplace to the right. And we're looking for the probability that somebody falls between those two values. So negative 1.9 has a percent of 2.87%. All right, so that means that from here this way, that is 2.87%. And then likewise, 0.4 is here, and it's 65.54%. So that would be from here backwards. And that would be 65.54%. So what I'm looking for is what's between them, this area here. So to do that, if 65.54 goes all the way to the left, and it's cut off by 2.87, then to find the percent between these two percentages, we're just going to subtract. So our answer is going to be 65.54 minus 2.87. 65.54 minus 2.87 for a grand total of 62.67. So we would expect, on average, that about 62.67% of the students would score somewhere between a 37 and a 67. So, recapping, if you're just looking for an answer to the left of the graph, you pull the number off the chart. If you're looking for an answer to the right on this graph or in a problem, you're going to subtract the chart's answer from 100. If you are going between two numbers, you find both percentages in the chart and you subtract them. Just realize that probabilities can't be less than 0, therefore they can't be negative. So if you just subtract them in the wrong order, get rid of the negative sign. Standard normal table and formulas for the spreadsheet's version of the normal table. Under Module 2, scroll down below where the notes are submitted, past Part 1 and past Part 2. And in Part 3, you will find how to use the normal distribution table. It's just a little video on it. You will find the percentile table here. So if you click on this, it'll take you to the percentile table. And below that is the spreadsheet formulas. So these are all the spreadsheet formulas for average, median, mode, quartiles, standard deviation. Just lose the P part here. Normal distributions, one with a z-score, one with data. Same thing for the inverse, one with the z-score. Gives you a z-score from a percent, the other one requires data. To find normal curve answers is a little bit more precise than that chart I was just working off of, because that one only went for z-scores rounded to the nearest tenth. This one will take it to almost 9 or 10 decimal places or something crazy like that. So how to work it is a little weird at first. It's a formula, so you're going to have to start off with an equal sign. And the formula from the sheet that you can find in Moodle is norm dist, which means the normal distribution. Now this is the one that'll take data to come up with the percentile, where another one will take just the z-score. So if you get confused about what needs to be where, you can click on that little question mark that I just did. It'll open up the informative part of this spreadsheet. It tells you that the first number has to be the mean, or the value you're interested in, I'm sorry. The second one has to be your mean. The third one has to be the standard deviation. And the cumulative, you're going to put 1. And what 1 means is just, it means to the left. But none of the numbers mean to the right, so just use 1 as the end. So for this one that says score below a 70, I'm going to type in 70, comma, then I need the mean. Now generally the mean is going to be calculated on a spreadsheet. Here I just typed it in, it's the exact same one as that math test. So there's the mean, and then comma. The next thing up is standard deviation, so hit that in there, and comma, and then the 1 to say to the left. And this should be the same answer that we got on the previous one. Now notice it's written as a decimal, so if we want it as a percent, you have to go up here and format as a percent. And depending on how many decimal places you want it to have, you can have less and you can have more to see how accurate we can get with it. So I generally do about 1 decimal place. All right, so that would be the formula for less than 70. It's just a straight pull off of the table. Now, if we want to go greater than 70, then we're going to have to do the 100 minus it. So it's going to be 100 minus norm dist, and then 70, and then mean, then standard deviation, and then 1. And, oops, sorry, 1 minus it. These come back as decimals, not as percent, so 1 represents 100%. I almost forgot that. All right, and we'll change this one into a percent too, and shrink the decimal down 1. All right, so the next example up is score below a 37. So that would be norm dist. So I'll do the 37, and then the mean, comma, the standard deviation, comma 1. And this will give me the below percent in a decimal format. So change it into a percent, and I'll shrink it down a little bit. All right. Well, of course, the answers previously were 2 decimal places. Neither here nor there. And then a score below a 67 would be norm dist, the 67, comma, the mean, comma, the standard deviation, comma 1. Now, these two answers in the previous example, we subtracted them. Whoops. Yeah, that's right. So this last answer is going to be the big one minus the small one. 62.3%. So let's see how this compares to what I did with the table. So a score below a 70 on the spreadsheet was 73.1%. On the by hand version using the table, it's 72.57%. So they're relatively close. It's just the spreadsheet one is actually much more accurate than the table version because we had to round that z-score to the nearest tenth. All right, then greater than 70 will be the same. It'll just be a little bit off. Here's the between probability. And the table said 65.54%. Our spreadsheet says 65% even. Our table said 2.87%, but our spreadsheet said just 2.7%. And then when we subtract them, we get 62.3. So it's relatively close to even the approximation of the table. So the spreadsheet just gives a better answer because it has a larger number capacity. So most z-scores will be looked like we did earlier. We would use the formula, come up with the z-score, and find the percentile. But sometimes we want to be able to go, well, backwards. So let's say we want to know what specific score on the test had a z-score of 0.8. Well, if that's true, then this formula still comes into play. And we just plug in the stuff that we know. I know the z-score now, so this side becomes 0.8 is equal to, I do not know what x is. I'm looking for a score that has a z-score of 0.8, minus the mean, which is 62, divided by the standard deviation, which is 13. Looks like algebra is going to come into play. So with a little bit of algebra, the first thing I would get rid of is this 13 in the denominator. To get rid of that 13 in the denominator, you're going to take both sides of the equation and literally just multiply by 13. So on the right-hand side, the 13s are just going to cancel. They're gone. You don't need to distribute the 13. It just turns into a big fat 1. On the right-hand side, we just have to figure out what 13 times 0.8 is. and it's 10.4. So we get 10.4 is equal to x minus 62. And then a little bit more algebra. We're trying to get x by itself, so I'm going to do the opposite operation on 62 to both sides of the equation. And I'll put a 0.0 there for emphasis. So this is going to become 52.4 is the score that I'm looking for. So 52.4 is equal to x. And we didn't even have to look at the table for this one. Now, eventually we're going to have to look at the table because I won't be telling you what the z-score is. I'll be telling you what the percent is. All right, so here's a problem where I want to go from a specific percent to either below or above a number to find a specific z-score, which will bring us to a specific, in this case, test score that will be a cutoff for A. So Mr. K wants to curve his tests. By the way, I never curve my tests. And he has determined that the top 15% of the class should have A's. What is the cutoff score for this A? So we know that the top 15% of the class is going to get these A's. And if we're looking at a picture of a normal curve, and this is probably one case where you really do want to draw the picture, the top 15% would be on the top tail. So these people you would expect to get an A on the test. And we're looking for this z-score that's associated with 15% above a z-score. The only problem is tables don't work on percents above. The table that we're going to work off of works on percents below. So the percent that is below a z is going to have to add up to with 15% to give you a total of 100. So the first thing we're going to have to do is take 100% and subtract our 15%, and that'll leave 85% of the class is going to score less than this z-score or have less than an A on the test. All right, so this is the number that we're going to have to look up on the table, 85%. All right, so when I pull up the table, I actually had to piece a couple of them together to get it on here. 85%, if we're looking at just the percentile columns, is somewhere in here. It's between 84.13 and 86.43. So basically what you have to do is figure out which one is closer to 85%. And if you do 85 minus 84, it's a little bit less than 1. If you do 86.43 minus 85, it's a little bit more than 1. So the closer number is actually z equals 1. So we're going to take this guy. Again, on a spreadsheet, it would be a little bit more accurate, but we're not being perfect here. So we're going to use a z-score of 1. So this cutoff score for z is going to be z equals a positive 1. And then I can go z is equal to x minus x bar over s and plug in what I know. So z is equal to 1. X is the cutoff score I'm looking for. X bar is 62. And the standard deviation is 13. And just like before, I'm going to multiply both sides by 13. Oops. And the 13s over here will cancel. And we'll be left with 13 on this side is equal to x minus 62. So if you're going to get an A after adding 62 across, that would be 75. You would have to have a score better than a 75. Well, I would say 75 or better to be safe. So anybody that scored a 75 or better on this test would receive an A. Now, let's talk about just a small topic of why I don't curve. Those that go to prestigious colleges like Cornell University in New York, it literally takes the top 0.05% of the best students in high school. So you take all these really smart people and throw them into one school, into one class, and technically they all know what they're doing, so you still have to give grades A through F to this class. So what they do is they curve it. And when they curve it, it forces certain people to have a A, and the cutoff for an A could be like a 98 on a test. And then the B could be somewhere between a 95 and a 98 and so forth and so on. So even though they might be scoring an 85 on a test, they could still be failing the test. So this is one reason that I'm not a fan of curving grades. All right, now Mr. K needs to cutoffs for B's, and by finding the B cutoff, you will technically find all of them, F, D, C, and B. So basically what I mean by that is if an A has a z-score of 1, then the F is also going to have a z-score of kind of a 1, except it's on the other end of it. You're going to have 15% of the class have Fs, and the z-score for that one is literally going to be a -1. So we can find out the F's just by knowing what the A's are. So if we do that, we're going to get -1 is equal to that score I'm looking for, minus that 62 average, divided by a 13 standard deviation, multiply both sides by 13, and we get this. So x is going to equal 62 minus 13 for a grand total of 49. So anybody that scores less than a 49 on this test will get a F on the test. All right, so that gives me two of the cutoff scores, a 49 for an F and a 75 for an A. So let me remind myself that this was a 75. All right, so then I want to find the B's. Now he wants 20% of the class to get B's, but that's not the top 20% of the class, it's just 20% of the class. But it is going to be right next to the A's. So to find the percent, we're going to have to take these two numbers and add them together, so that's 35%. So that's what I need to look at the table. The ZB, 30% of the people, 35% of the people are going to score better than a B or better, a B or better. So if 35% are going to score better, then what we need to do is find out how many are going to score less than a B. So that would be 100 minus 35, which is 65% of the class. So on the table, I need to look up the percent 65. So the closest number to 65% on the table is this one right here. There's no doubt about it. It's only 0.54 away. And it is associated with the z-score of 0.4. So this ZB is going to be 0.4. And then we kind of just set it up off to the side. 0.4 is equal to x minus 62 over 13. We're going to multiply both sides by 13, so 13 times 0.4 is 5.2. So this becomes 5.2 is equal to x minus 62. And if we add 62 to both sides, we're ending up with 67.2. So the ZB is associated with 67.2 as a score, and the F was 49. Now to find the grade associated with a D would be on the other side of the curve over here. Let's put it there. And its z-score would be negative 0.4. And this will be the last one I need to find. So negative 0.4 is equal to x minus 62 over 13. If we multiply both sides by 13, you still get 5.2. It's just that it'll be negative this time around. And then 62 minus 5.2. Couldn't do it in my head. 56.8, let's put it at 57. So this score, to create a D, would be a 57. Close enough. So that leaves one grade, and that grade is the most common grade. Technically, if you do it by the 68, 95, 99.7 rule, that should be about 68%. But in this case, I don't think it is. It's 30% because there's 35% to the right, and that'll get B or better, and 35% to the left, that will get D or less. And then therefore that's 70%, and it only leaves 30% for the C's. But therefore we know the breakdown of all the grades. If you score less than a 49, you're going to get an F. If you get a score less than a 57 to a 49, you're going to get a D. If you score between a 67 and a 57, you're going to get a C. If you score from a 75 to a 67.2, it's a B. And anybody above a 75 gets an A. So this is how curves work. We just did it by hand to break down and curve a score. So let's see how the spreadsheet will do it. And you'll find that it's much easier than what we did by hand. So the function that we're going to use for this one is called norm inverse, INV. So what a norm inverse takes is a x value. Now this x value is input to the inverse normal distribution function. It's not the same as the x value of a norm dist. That would be a data point. So this x value is literally the percentile that you want. So the top 15% of the class, remember, it's got to be the reverse of that. So in here I'm going to type in 1 minus 0.15. That'll represent the 85% of the class that's not going to get an A. All right, the next thing up is the mean, and then the next thing up is the standard deviation, and that's it. This will tell us what score you need to have to be in the top 15%. Oops, I still have the cell as a percent. I want it as just a number. So just like what we found by paper, it was about a 75. The next 20%, we would have to do norm inverse, and 20 plus 15 is 35, so we'd be doing 1 minus 0.35, comma the mean, comma the standard deviation. And again, I have that as a percent still, so number. And that gives me the score that I need to score a B on, 67 or higher. And that's pretty close to what I got. Yeah, it's very close to what I got by hand. So this is much easier to work with. It's just you have to think about what's going on with the picture even before you do it in a spreadsheet to understand that you have to do 1 minus, because we're not talking about the top part of the curve with a normal distribution. We always talk about the bottom part.